question at hand involves the appropriate sizing of branch circuit conductors and overcurrent protection for an heating, ventilation, and air conditioning unit. Specifically, the scenario presents a situation where number 12 THHN conductors are proposed for a branch circuit protected by a 25 amp breaker in a panel board, feeding and heating, ventilation, and air conditioning unit with a fuse disconnect. The core concern is whether this configuration adheres to the National Electrical Code, and if any exceptions permit the use of a 25 amp breaker with number 12 conductors in this application. The short answer is no. There are no exceptions that allow for a 25 amp breaker on number 12 THHN conductors for a branch circuit to an heating, ventilation, and air conditioning unit with a fuse disconnect. The National Electrical Code mandates that branch circuit conductors be sized according to the overcurrent protection device protecting the circuit. For a 25 amp breaker, the minimum wire size for THHN conductors is number 10 per table 310.16 of the National Electrical Code. To elaborate further, let's dissect the relevant sections of the National Electrical Code. Firstly, National Electrical Code Section 310.16 dictates the allowable ampacities of insulated conductors rated up to and including 2000 volts. This table provides the ampacity ratings for various conductor sizes based on insulation type and temperature rating. For THHN conductors, which are commonly used due to their heat resistance and suitability for dry and damp locations, the ampacity is determined by the conductor size. Secondly, National Electrical Code Section 240.4d addresses the protection of conductors. This section generally prohibits overcurrent protection from exceeding the ampacity of the conductors being protected. However, exceptions exist, particularly for specific applications such as motor circuits and heating, ventilation, and air conditioning equipment. Thirdly, National Electrical Code Section 440 pertains specifically to air conditioning and refrigerating equipment. It outlines the requirements for disconnecting means, branch circuit overcurrent protection, and motor compressor overcurrent protection. Within Article 440, Part 3 deals with disconnecting means, while Part 6 covers other considerations. National Electrical Code Section 440.32b requires branch circuit conductors for heating, ventilation, and air conditioning equipment to be sized per Table 310.16. The National Electrical Code references cited do not provide any exceptions or modifications to the requirement that number 12 THHN conductors are not adequately protected by a 25 amp breaker. Let's delve deeper into why a 25 amp breaker is not permissible for number 12 THHN conductors in this scenario. The primary reason is the ampacity rating of number 12 THHN conductors. According to Table 310.16, number 12 THHN conductors typically have an ampacity of 20 amps when installed in race whizzer cables and are rated at 75 degrees Celsius. This ampacity is based on the conductor's ability to dissipate heat without exceeding its temperature rating. If a 25 amp breaker is used to protect number 12 THHN conductors, the breaker may not trip in the event of an overload condition where the current exceeds 20 amps but remains below 25 amps. This sustained overload can cause the conductors to overheat, potentially damaging the insulation and creating a fire hazard. While it's true that some exceptions exist for motor circuits, allowing for overcurrent protection to exceed the conductor ampacity under certain conditions, these exceptions are carefully defined and do not apply to general branch circuits for heating, ventilation, and air conditioning equipment. These exceptions typically involve specific types of motor protection, such as time delay fuses or inverse time circuit breakers, which are designed to accommodate the motor's starting current surge without nuisance tripping. In the case of heating, ventilation, and air conditioning equipment, the overcurrent protection requirements are generally more stringent due to the continuous nature of the load and the potential for overheating. To ensure compliance with the National Electrical Code and maintain electrical safety, it's crucial to select the appropriate wire size for the given overcurrent protection device. In this scenario, with a 25 amp breaker, the minimum wire size for THHN conductors is number 10. Number 10 THHN conductors typically have an ampacity of 30 amps, providing adequate protection for the circuit. It is worth noting that the ampacity ratings in Table 310.16 are based on specific conditions, such as the number of current-carrying conductors in a raceway or cable, the ambient temperature, and the termination temperature rating of the equipment. Adjustment factors may be required if these conditions deviate from the standard assumptions. For example, if multiple current-carrying conductors are installed in a raceway, the ampacity of each conductor must be directed to account for the increased heat generated by the group. Similarly, if the ambient temperature exceeds 30 degrees Celsius, the ampacity must be adjusted downward. Furthermore, the termination temperature rating of the equipment must be considered. If the equipment is only rated for 60 degrees Celsius, the ampacity of the conductors must be based on the 60 degrees Celsius column in Table 310.16, which may result in a lower ampacity rating. In summary, the National Electrical Code requires that branch circuit conductors be sized based on the overcurrent protection device protecting the circuit. For a 25 amp breaker, the minimum wire size for THHN conductors is number 10 per Table 310.16. The references cited do not provide any exceptions or modifications to this requirement. Therefore, the use of number 12 THHN conductors with a 25 amp breaker for a branch circuit or in heating, ventilation, and air conditioning unit with a fuse disconnect is not permitted by the National Electrical Code. Always consult the latest edition of the National Electrical Code and consult with a qualified electrical professional to ensure compliance with all applicable codes and standards. To further illustrate the importance of proper wire sizing, consider the potential consequences of using undersized conductors. Overheating of conductors can lead to insulation breakdown, which can cause short circuits, ground faults, and ultimately electrical fires. Additionally, voltage drop can become a significant issue with undersized conductors, particularly over longer distances. Voltage drop occurs when the voltage at the load is lower than the voltage at the source due to the resistance of the conductors. Excessive voltage drop can cause equipment to malfunction, operate inefficiently, or even fail prematurely. In the case of heating, ventilation, and air conditioning equipment, voltage drop can affect the performance of the motor compressor, reducing its efficiency and lifespan. To minimize voltage drop, it's essential to select conductors with sufficient ampacity and consider the length of the circuit. The National Electrical Code provides guidelines for calculating voltage drop and recommends limiting it to a maximum of 3% for branch circuits and 5% for feeders. In addition to wire sizing, the selection of appropriate overcurrent protection devices is crucial for electrical safety. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors and equipment from excessive current, which can result from overloads, short circuits, or ground faults. Circuit breakers are resettable devices that trip automatically when the current exceeds a predetermined level. Fuses, on the other hand, are one-time devices that melt and interrupt the circuit when the current exceeds their rating. The selection of overcurrent protection devices should be based on the ampacity of the conductors being protected, the characteristics of the load, and the interrupting rating of the device. The interrupting rating is the maximum fault current that the device can safely interrupt without failing. It's essential to ensure that the interrupting rating of the overcurrent protection device is sufficient for the available fault current at the point of installation. In summary, proper wire sizing and overcurrent protection are fundamental aspects of electrical safety. The National Electrical Code provides comprehensive guidelines for selecting conductors and overcurrent protection devices to ensure the safe and reliable operation of electrical systems. Always consult the latest edition of the National Electrical Code and consult with a qualified electrical professional to ensure compliance with all applicable codes and standards. Let's recap the key points regarding the use of number 12 THHN conductors with a 25 amp breaker for an heating, ventilation, and air conditioning unit branch circuit. Firstly, the National Electrical Code requires that branch circuit conductors be sized based on the overcurrent protection device protecting the circuit. Secondly, for a 25 amp breaker, the minimum wire size for THHN conductors is number 10 per Table 310.16. Thirdly, the use of number 12 THHN conductors with a 25 amp breaker for a branch circuit to an heating, ventilation, An air conditioning unit with a fuse disconnect is not permitted by the National Electrical Code. Fourthly, overheating of conductors can lead to insulation breakdown, short circuits, ground faults, and electrical fires. Fifthly, voltage drop can become a significant issue with undersized conductors, affecting equipment performance and lifespan. Sixthly, overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors and equipment from excessive current. Seventhly, always consult the latest edition of the National Electrical Code and consult with a qualified electrical professional to ensure compliance with all applicable codes and standards. The information provided in this narration is intended for general guidance only and should not be considered a substitute for professional electrical advice. Electrical work should always be performed by qualified individuals who are familiar with the National Electrical Code and local codes and regulations. Improper electrical work can be dangerous and may result in serious injury or property damage. In addition to the topics discussed thus far, it's worth mentioning the importance of proper grounding and bonding in electrical systems. Grounding and bonding are essential for providing a safe path for fault current to return to the source, allowing overcurrent protection devices to trip and clear the fault. Grounding involves connecting the electrical system to the earth, typically through a grounding electrode such as a ground rod or metal water pipe. Bonding involves connecting all non-current carrying metal parts of the electrical system together, such as metal conduits, enclosures, and equipment frames. Proper grounding and bonding help to minimize the risk of electric shock and prevent the build-up of static electricity. The National Electrical Code provides detailed requirements for grounding and bonding, including the size and type of grounding and bonding conductors and the methods of connection. It's essential to follow these requirements carefully to ensure a safe and effective grounding and bonding system. Another important consideration in electrical system design is coordination. Coordination refers to the selective tripping of overcurrent protection devices to minimize the extent of an outage in the event of a fault. Ideally, only the overcurrent protection device closest to the fault should trip, leaving the rest of the system unaffected. Coordination can be achieved by selecting overcurrent protection devices with appropriate time current characteristics such as inverse time circuit breakers or time delay fuses. Inverse time circuit breakers trip faster as the current increases, while time delay fuses allow for temporary overloads without tripping. Proper coordination requires careful analysis of the electrical system and coordination studies to determine the optimal settings for overcurrent protection devices. In addition to the technical aspects of electrical system design, it's also important to consider the environmental conditions in which the system will be operating. Environmental factors such as temperature, humidity, and exposure to corrosive substances can affect the performance and lifespan of electrical equipment. For example, in hot environments, the ampacity of conductors may need to be directed to account for the increased ambient temperature. In humid environments, corrosion-resistant materials may be required to prevent deterioration of electrical connections. In corrosive environments, special enclosures and coatings may be necessary to protect electrical equipment from damage. The National Electrical Code provides guidance on selecting electrical equipment for various environmental conditions. Finally, it's essential to maintain electrical systems properly to ensure their continued safe and reliable operation. Regular inspections and testing should be performed to identify any potential problems, such as loose connections, damaged insulation, or malfunctioning overcurrent protection devices. Maintenance tasks such as tightening connections, replacing damaged components, and testing overcurrent protection devices should be performed as needed. Proper maintenance can help to prevent electrical failures, extend the lifespan of electrical equipment, and maintain electrical safety. In conclusion, the design, installation, and maintenance of electrical systems require careful attention to detail and a thorough understanding of the National Electrical Code and other applicable codes and standards. Always consult with qualified electrical professionals to ensure that electrical work is performed safely and correctly. Remember, safety is paramount when working with electricity. Always to energize circuits before working on them, use appropriate personal protective equipment, and follow safe work practices. Electricity can be dangerous, but with proper knowledge and precautions, it can be used safely and effectively. In this narration, we have explored the specific question of whether a 25 amp breaker is permissible for number 12 THHN wire to an heating, ventilation, and air conditioning unit, and we have provided a detailed explanation of the relevant National Electrical Code requirements and considerations. We have also discussed broader topics such as grounding, bonding, coordination, environmental conditions, and maintenance. By understanding these concepts and following the guidelines of the National Electrical Code, you can help to ensure the safety and reliability of electrical systems. Remember to always consult with qualified electrical professionals for specific advice and guidance on electrical projects. The information provided here is intended for educational purposes only and should not be considered a substitute for professional electrical advice. The field of electrical engineering is constantly evolving, with new technologies and codes being developed regularly. It is essential to stay up to date with the latest advancements and best practices to ensure that electrical systems are designed, installed, and maintained safely and effectively. Continuing education and professional development are crucial for electrical engineers and technicians to maintain their competence and stay ahead of the curve. There are many resources available for electrical professionals to enhance their knowledge and skills, including industry conferences, training courses, and online resources. By investing in their professional development, electrical professionals can contribute to the advancement of the field and ensure the continued safety and reliability of electrical systems. The commitment to safety and excellence in electrical engineering is essential for protecting lives and property and for supporting the critical infrastructure that powers our world. The topics discussed here are just a small part of the vast body of knowledge that comprises the field of electrical engineering. There are many other areas of specialization, such as power systems, control systems, electronics, and communications. Each of these areas requires specialized knowledge and skills, and electrical engineers often focus their careers on a particular area of interest. Whether you are an electrical engineer, a technician, or simply someone interested in learning more about electricity, there are countless opportunities to explore and expand your knowledge. The world of electricity is fascinating and complex, and there is always something new to discover. The information provided in this narration is intended to serve as a starting point for your exploration and to inspire you to continue learning and growing in your understanding of electricity. Remember to always prioritize safety and to consult with qualified electrical professionals for specific advice and guidance on electrical projects. With a commitment to safety, knowledge, and continuous learning, you can contribute to the safe and effective use of electricity in our world. This concludes the narration on the topic of heating, ventilation, and air conditioning branch circuit breaker size and wire gauge. We have covered the relevant National Electrical Code requirements, considerations, and best practices, and we hope that this information has been helpful and informative. Thank you for your attention, and remember to always prioritize safety when working with electricity.